This is our project, the HotWatch. Our project helps prevent the newly visually impaired from getting burned by alerting them of a heat hazard. This is useful, especially when they are learning to do household duties such as cooking. Below are some statistics showing the necessity for our product. The IR temperature sensing camera will read the measurements perpendicular to the wrist. It will read the data in a 4x4 segment area and sends the data to the microcontroller through an I2C connection. The microcontroller will read the data. If the temperature is above 52 degrees Celsius, which is the burning point of skin, the vibration unit will alert the user. The vibration unit will use a normally open relay so that only if the relay closes, the vibration unit will activate. This picture shows the setup of our prototype. The power source will supply 5 volts to the PIC microcontroller and the temperature sensing camera. The camera processes temperature data in its own IC and then transmits that data through I2C connection to our MCU. If the PIC microcontroller detects a temperature at or above 52 degrees Celsius, then through an I/O pin it will send a signal to the normally open electromechanical relay to switch and close to allow 5 volts to pass through the vibration unit and alert the user. The camera and microcontroller are connected with the serial data line and clock line to the RA2 and RA1 on the microcontroller. Pull-up resistors of value 4.7 kiloohms are connected between the 5 volts and SCA and clock lines. Here is the demonstration of the prototype. As the flame gets further away from the temperature sensing camera, the camera is still able to sense the high temperatures and excite the vibration unit. The parts from the breadboard will be soldered onto a PCB, making a small and compact design. The vibration disc will be located closest to the skin, with it encased to assure the vibration won't affect the other components. The PCB will have the microcontroller and relay soldered onto it in the middle compartment to reach both the camera and the disc. The camera temperature sensor will be located on the outermost layer at a 90-degree angle from the wrist. There will be a 3D printed encasement and a wristband with Velcro to allow adjustability. For part of the hardware test, different thicknesses of 3D printed materials were tested with the vibration unit at multiple voltages to find the optimal vibration strength and the band that gave the most comfortable fit. It was concluded that a 5-volt strength and a 0.3 mm thickness was optimal for comfort and alerting the user. We began the camera test by changing the angle on the camera in intervals of 15 degrees at a distance of 11 centimeters. It was concluded that at an angle of 90 degrees, the most accurate temperatures were recorded. Using the results from the angle tests, different distances were tested at a 90-degree angle using a height gauge and hot plate connected to a thermocouple. As the height increased, the camera became more inaccurate as seen with the percent error increasing. For the first stage prototyping, we used the Arduino to simulate data flow from the temperature sensing camera to the rest of the circuit. The output is a 16-segment display as seen on the screen. Before a flame is lit, the numbers show various room temperature values. Once the flame is placed in front of the camera, the display begins to show values corresponding to the higher temperatures.